limit n goes to infinity, or maybe this will become plus 1/2. So this will become L prime of t. So if I take this power down, so this is going to be n power 2 minus 3/2. Okay. So this will become 1/2 of limit n goes to infinity L prime of t over square root of n. Okay. T over square root of n divided by n power 1/2. So it's going to be 2 down to 4 minus 1, 3 n power 1/2. Still, this would be a troublemaking term actually. So, 5. This is negative 2, and this would be plus 3. So this would be minus 1/2 actually. Okay, this would be minus 1/2. Because n power 2 will become n power negative 2, minus 3/2 will become plus 3/2, and you're going to get this. So again, this is, if I, for example, compute the limit, so it's going to be L prime of 0 divided by, 1 over infinity, or 1 over the denominator that goes to infinity. So this is 0 and this is 0 as well, because L prime of 0 is also 0. So again, this is like a 0 by 0 form. So what you can do, again apply the L'Hopital rule. So if you can again apply L'Hopital rule, what are you going to get? You're going to get L double prime of t over square root of n times, by the way, here there should be also t. Okay? There should be also t, so this would be t, and this would be t upon 2 as well. Okay? So keep a check on my calculations. So keep your eyes open always. Okay? I'm bad at calculations. So L double prime of t power n, and again this will become minus t half times n power minus 3/2. Okay, the same, because t over square root of n has this derivative, divided by minus 1/2. Okay, minus 1/2 and n power minus 3/2. Okay, n power minus 3/2. Now what is the good thing that happens? The good thing that does happen is that now you can get rid of this power. So these two will be cancelled, 1/2 will be cancelled with 1/2, 1/2. So what you're going to get? You get, obviously you need to take the limit, n goes to infinity. So what you're going to get? T multiplied by t upon 2, so this is t square upon 2, times L double prime of 0. L double prime of 0. And what is L double prime of 0? This is exactly what you call 1. So the final outcome that you get is called t square. Now what we have shown, let's collect this. What we have shown so far. So I have shown that n multiplied by L of t over square root of n, which is basically equal to n log of m of t over square root of n, this converges to t square over 2. Okay? This converges to t square over 2. That is, I can say that log of m of t over square root of n power n converges to t square over 2 as n goes to infinity. So if I take, for example, exponential on both sides, that is, what does this shows? That m of t over square root of n power n converges to the e to the t square over 2. And what do you remember now? This guy is precisely equal to the moment generating function of Sn of t. And this guy is precisely equal to the moment generating function of the standard normal distribution. So what we have already proved, we proved that the moment generating function of Sn converges to what? Converges to the moment generating function of what you call a standard normal random variable actually. And hence, what does this shows? That the distribution function of Sn converges to the distribution function of the standard normal distribution. Okay? So we proved it as n goes to infinity. But we proved it for the case when mu is 1 and sigma square is 1 actually. Now consider the generic case. Okay? I want to deduce the generic result from this result. We have the central limit theorem for i.i.ds when the mu is 1 and variance is 1 actually. Mu is 0 and variance is 1. Okay? Generic case, general case. General case. Consider xi star, a sequence of random variable xi star that is denoted by what? Xi minus mu divided by standard deviation. Okay? Standard deviation. Now, what can I say about xi star? So the xi star, okay? Xi star, by the way, by general case, I mean that now mu is not 0 and sigma square is not necessarily 1. In other words, mu is not necessarily 0 and sigma square is not necessarily 1 actually. So they are general, they can be anything. Now if xi star is xi minus mu over sigma, so this is like a standardized version of xi. Okay? The standardized version of xi where the expectation of xi is mu and the variance is sigma square. What would be the expectation of xi star? The expectation of xi star is going to be the expectation of xi minus mu divided by sigma. Okay? So it is going to be expectation of xi minus mu divided by sigma. But expectation of xi equals to mu. So this means that this is equal to 0. This is equal to 0. And what is the variance of xi? Let's compute the variance of xi star. So the variance of xi star is really, okay, variance of xi star is variance of xi minus mu divided by sigma, which is going to be, okay, you pull out this sigma out, so sigma squared, and is going to be the variance of xi minus variance of mu, which is 0. But the variance of xi is sigma squared over sigma squared, which is 1 actually. So what do I know about xi star? So xi star is standardized version of xi, and they have mean 0 and variance, what do you call 1. We have already proved that for such random variable which has the mean 0 and variance, what do you call 1, you already have proved the central limit theorem. We already have proved the central limit theorem actually. So in other words, if I take the moment generating function of sum of xi star, or maybe I do this calculation before, so let's calculate xi star divided by the square root of n. Okay? This is equal to sum, that say goes from I equal to 1 to n, xi minus mu upon what do you call sigma and everything divided by square root of n. I can take this sum, so it's going to be sum of xi I equal to 1 to n xi minus sum of the mu's, so it's going to be n mu divided by the square root of n and sigma, which is equal to precisely Sn in our general case actually. Okay, in our general case. Now, if I want to take the moment generating function of Sn of t, this is same as the moment generating function of sum of xi star upon square root of n of t. Okay, but for such a sum, for such a standardized sum, we have already proved by central limit theorem that this converges to phi to what do you call e to the t square upon 2 as n goes to infinity. Okay, we have proved that the moment generating function of the sum of random variables which have mean 1 and variance 0, or mean 0 and variance 1 divided by the square root of 1, its moment generating function converges to the e to the t square over 2. But moment generating function of sum of xi square divided by square root of n is equal to the moment generating function of Sn, because this is equal to Sn. So we kind of showed that the moment generating function of Sn converges in general to the e to the t square over 2. That's a moment generating function of a standard normal distribution. And if this is the case, then by this lemma we proved again in the general case that the distribution function of Sn converges to the distribution function of what you call a standard normal random variable actually. And this really completes the proof of theorem. We have proved the what you call the central limit theorem.